So we'll get started with the first presenter, Chris Chambers from Meter Group. He's going to be exploring the limits of complex dielectric through intersections in technology.
Thank you, everyone. Oh, make sure I got my.
Yes, I should.
Can I advance here?
So you're going to hit up and down.
Up and down.
There you go.
All right. Thank you very much. I heard someone yesterday say that we don't need any more sensors. If that's the case, this is a little awkward. No, but really, I'm going to make the case for why we need one more sensor. Just one more, right? The last sensor. But I'm here to talk about a new sensor technology today for which we really are exploring the limits of. Okay, never mind, I got it. Yeah. Thank you. And the reason why we need a new technology is that 20% of the world's arable agriculture or arable land is salt affected. And by salt affected, they mean that the saturation extract electrical conductivity is greater than 4 decisiemens per meter. Now, we use electrical conductivity as a proxy for salt to measure a time series of it. And the real problem is that many dielectric sensors, many sensors that use the electrical properties of the soil to measure water content are also interfered with by salt. And this varies from sensor to sensor. I'm going to use our sensors as an example. The Teros 12 has loses its the calibration gets wonky at about 10 decisiemens per meter saturation extract EC. And also to measure the salts in the soil, we need a new technology and more accurate sensors. Thank you. It's okay. And this isn't unique to the Teros 12 or capacitance sensors. TDR, FDR, basically every sensor that uses some technique like this has some salt limit, which can really be a problem if you're trying to manage water, which after a long enough drought or in an arid enough environment is synonymous with managing salts. So being able to measure the water content, but also being able to measure that salt better is the reason we're exploring this new technology. So a couple of definitions before we go further. The bulk EC, electrical conductivity, that's what the sensor gives you. And that includes the soil, the air, the water, and the solutes in the water. So it's really hard to get at just what's affecting that value. But that's what the sensor can do. The pore water EC is really what more people are interested in. That's the salt concentration of the soil, the water in the soil itself. That's what most people want when they're looking at the EC data. You usually need a model to get at that. And then the saturation extract EC is what you're going to get from most of your soil lab analyses. That's adding some DI water until you get something that you can actually measure the electrical conductivity of a solution. So each of these three things is going to factor in today. And here's the electrical conductivity, or here's the water content of a Teros 12. Like I said, this calibration gets all wonky at about 10 decisiemens per meter saturation extract EC. And on the graph down low on the right, we've got measured VWC on the x-axis and the actual VWC verified gravimetrically on the y. And look for those gray dots above the 1-to-1 line. There's a couple of dots floating way up there. Those are 50 decisiemens per 50 decisiemens per meter water and 30 decisiemens per meter water. Really saline conditions. And the VWC measurements from this Teros 12 are not going to be reasonable, right? That salt is too high. The water content isn't a valid value. And this is really common in salt-affected soils. So let's look at the soil from the sensor perspective for a minute. I've only got 2 technical slides, so bear with me here. We're going to get through it. But the soil is looking, or the sensor is looking at the soil like it's a circuit with a conductance and a capacitance in parallel, right? And so the capacitance, that CS at the top, that's what's giving you your water content. And that conductance at the bottom, So you're trying to measure this capacitance to measure water content. And if that conductance is low enough, that works great. If that conductance gets high, you're basically trying to measure a leaky bucket. So you're leaking electrons out of this conductance while you're trying to measure the dielectric. So we've taken a really complex math problem and turned it into a geometry problem. And the red arrow on the right is what we really want. The x-axis is our conductance component. The y-axis is our dielectric or our capacitance component. And together, taken together, they have a function that gives you complex dielectric. And this is called the admittance plane. It's just the admittance to an electromagnetic field. Now, where our new sensor technology comes in is you've got this fancy circuit diagram on the upper right. The only thing you need to worry about are the R component and the C component, right? Those are the capacitance and the conductance. But what we get from each of these components in our admittance plane is a circle of all possible solutions. So just take that circle on the right, the orange circle. If we're just measuring resistance or conductance, then the solution for complex dielectrics is anywhere on the edge of that circle. But adding these other components and measuring them simultaneously, the complex dielectric is found at the intersection of these three circles. That's why we call the technology complex dielectric through intersections, because we've taken this math problem and made it a geometry problem, or CDX for short. And so this really, if you look at, we've got the SOLYX 14. I didn't think about my formatting very well. I swear I have done this before. Lessons learned for the future for formatting. But that 50 decisiemens water for the SOLYX 14, which is our new CDX sensor, it falls right within that 1-to-1, within the plus or minus 5% error of the 1-to-1 line. So there's a little bit of an offset high on the new CDX technology, but compared to the Teros 12, it stays within the plus or minus 5% error at those higher electrical conductivity. So the problem of higher electrical conductivities is completely solved. It's not completely resistant to electrical conductivity, but it's much improved, especially at the higher conductivities of the water. And I want to talk about measuring pore water EC here, because measuring the water content, that's great. That's a huge step forward for salt-affected soils, but also measuring this pore water EC. And so we're using the Hill-Horst model from 2000 for that. And the numerator in this term is the dielectric of water in the soil times the bulk dielectric, which what you get from your sensor, divided by basically the difference of dielectric. That epsilon B is the bulk dielectric that you get from your sensor. And that epsilon sigma B, that's a soil-specific term. In this, it's assumed to be 4.1. So this is the basic model to calculate pore water EC. And for our new CDX technology, we started out in rock wool because soil is really hard. It's really complex to get a handle on. But rock wool's, it's a really simple substrate. It's a lot just like basically the fiberglass insulating your house. So using this pore water model with our CDX technology, it's really accurate. So we're getting easily within plus or minus 1 decisiemens per meter across these different electrical conductivity levels. And so these are known electrical conductivities that we're putting in this rock wool slab. Plus, there's no antecedent salt conditions with the rock wool, which makes it a lot easier to get a handle on. And when we go to soil, I'm going to start with the error term because the error really tells the story of measuring pore water EC with dielectric sensors frequently. Note the gray dots are the Teros 12, and the blue dots are our CDX, our new CDX sensor. And less than 15% water content, right? So this is what we're looking at with the dots is the difference between a known EC concentration and the pore water EC measured by the sensor over a range of water contents. So we got VWC on the x-axis and then the error on the y-axis. So the gray dots, less than 15% water content, they're all over the place. We've got one hanging out at about 200 decisiemens per meter at low water contents. That's an extreme outlier, but you can just see that the scatter, the uncertainty in the TEROS 12 really makes it where this model is unusable at low water contents. And we recommend that you throw any TEROS 12 data below 10%, below 15% VWC, just throw it out. The new CDX technology is making that much more reliable, where the error is not very much increased, down to about 5% VWC. And so throwing out, let's see, I threw out everything less than 10% water content for this slide. And the red bars are the known pore water electrical conductivity. And there's some overestimation at low levels and some underestimation at high levels of EC. So we really are exploring the limits of the new sensor here. It's a big improvement in many ways, but we still have some things to figure out, especially when it comes to measuring the pore water electrical conductivity. But we're getting much, much better results than the TEROS 12. Moving on, there is a strong soil component too. So we're taking the TEROS 12 right out of this and just looking at our new CDX sensor. The blue on the left is a sand, and then the gray ones to the right are a sandy loam. And so the sandy loam has an offset at the lower electrical conductivities, and this is across water contents. And thinking back to this pore water model where epsilon sigma B is a constant, it might not be doing us justice at this stage. We might need to tweak that a little bit to get better estimates of pore water electrical conductivity. So in conclusion, I know the first thing y'all are thinking, do I need to run out and replace my entire sensor network with CDXs right now? That's not the goal of the sensor. And we're still really learning about the limits of what it can do. When you use it head-to-head with other water content sensors, it looks really good in our preliminary studies. But it's a new tool for the toolkit, especially for high salinity soils. We've got a lot more work to do. We need to do more soils. Notice we didn't even touch clay yet. I don't know what that's going to look like, but it's going to be interesting. But then there's also possibilities for a more mechanistic volumetric water content calibration. We've got a lot to do, but it's a really exciting technology and happy to share it with you all.